The theory from this lab comes from two principles, Torricelli's principle and Bernoulli's principle. Torricelli's principle states that the velocity of a fluid equals square root of 2 times gravity times height. We want the average velocity, which equals 2 times gravity times the average height. Bernoulli's principle states that the buoyant force equals the density of the fluid times gravity times the volume of the fluid that's being displaced. In this experiment, we filled up a container with water and placed a piece of styrofoam, which we just approximated equals 0 grams, and put a weight on it. For the first one, we'll just say we used 100 grams. Then, because of that added weight, the volume of the water is going to be displaced and the height is going to increase. You need to solve for the volume displaced by taking the mass of the object and assuming that it has the density of water to get the volume displaced. So the height increases by the volume displaced over the area of the container. And then we can use this new initial height into the velocity formula.
Okay, so for this experiment, we filled up this container with water up to a height of 7.5 centimeters, all while plugging the hole at the bottom closed with our finger. We then placed a piece of styrofoam on top and placed the mass on top of the styrofoam and pulled up a graduated cylinder under to catch the water. For all trials, we took the time and took the water to flow it out until the graduated cylinder read 200 milliliters. Then we quickly plugged the hole back up. And we repeated the same process for first no weight, then 100 grams, 200 grams, 300 grams, and finally 400 grams.
After figuring out how the added weight influences the speed, which is by increasing the initial height, we plotted the time versus the average height graph and found only a percent error of 1 for the power, since the expected value was negative 0.5.
Thank you guys for coming over. We're just great that you're here because here actually we're discussing a topic in physics that was kind of weird. So we were talking about pressure a lot, and actually we were not sure if pressure, like if I were to have, like for example, a container of water, and I fill it with water, the water would be here, but the pressure would be different here. So if we were to make a hole through the bottom, we were asked the question of how fast the water could go through the bottom. What I want you guys to do, since I'll show you the cups in a bit, I just need you two guys for each to just put this meter to 700 milliliters. So, alright guys, so you guys put it at 700, that's perfect, because what I'm asking you to do next, I'm gonna uncover the jacket and I'll show you 3 receipts, and they're gonna give you, let's say, how many seconds here? 20 seconds. Yeah, to choose, just to choose something. And I mean, if you don't get to choose it fast enough, you just have to go with it. 3, 2, 1, go! 5, 4,
Wait,
3, 2.
what do they have?
I want that one.
I want
Actually, I'll take that one.
Wait.
Okay, I don't know.
Okay, I want that one. I got that.
Wait. It's fine. Try to.
What do you mean when it's hard?
Just lock in. Just like to like.
So go. 3, 2, 1, go! Alright.
Come on.
So we're seeing. So hold your pressure bets. Let's run over what's going on.
So if you want to find the time that it would take out to drain this whole container down, you would actually need to start from Bernoulli's principle. The Bernoulli's principle, I read that whole equation that is equal to the So now that we have the whole expression written out, you actually notice that it has a very similar shape or contour to what's actually the energy conservation form. So you'll see as the energy form, we have some sort of external work. Normally it's represented by a W, but in this case we have a P. Since this water at the top would be in contact with the atmosphere, it has a pressure that is equal to the atmosphere pressure. But also you'll see that the water at the bottom is in contact with the pressure of the environment. So we'll have the same pressure across them. So in this case, because they have the same pressure, these terms will just cancel out. We also have that an H2 and an H1, H1 being our initial height. So that would be the height of the water when it's on the top. So when the water has reached at the bottom, since this H is in terms of the depth of the water, so we'll see that it has emptied out. So actually H2 would be at the bottom of the container. So this H2 can also go away. So now let's take a look at this V right here, this V1 and V2. We know for certain that the water at the exit has to escape at a rate velocity, well, otherwise it would be like right, if I just were to put my finger, the water would be stationary, but the water has to empty out. So the water will be dripping out at a certain velocity, so that's the velocity we're trying to find. But we'll see that the water at the top is actually draining very slowly. And this becomes very important when we do the integration, because we'll see that this is actually a very infinitesimally small amount of change when we do the integration. So we'll see that for our calculations, we'll see that the V1 speed would be equal to 0, so that terms also cancels out. So I see something in common right here. I see that the densities are in common, and you just get that the h1 times the constant of gravity is equal, if we had to pass the 1/2 over there, and I have a square root and pass it to the other side, so my final velocity would be equal to 2h1g square root. Conservation of mass tells us that the changes in volume of the container and the one that we collect are supposed to be the same. So if we were to write that into a form of an equation, we'll just create that the changes should be equal to each other, because the same amount that I'm losing volume is the same amount that I'm gaining volume. So I can just say that the integration process of the V times the area times the H is going to be equal to the little change in the area times the velocity times dt. But if you were to think about the small orifice that is at the bottom, you would actually see that this is the area, this is the velocity, and since this velocity is actually expressing the terms of the little particles that are flying by the exit velocity, you can think, oh, but that can be any particle in the circle. So that actually gives you the velocity of the circle. And this dt would increase actually to give you the height of that cylinder, because as the velocity of the circle is going down, it's multiplying by a t term. That just means that it's giving you the flow of water that is going out the tube. And since the velocity is increasing or decreasing, the flow will increase or decrease. So if we were to set this equal to each other, that's dh equal a times v times dt. So if we were to solve this differential equation, we'll just put everything to the other side. This pi and this pi will cancel. We have the r squared and the b, and this y squared and the s right here. And we have the 2hg square root, the dh, and we only want to integrate this term because it's a constant, and we'll get the dt. And if you were to solve this integration, it will give you this expression right here. So we have that the time is going to be equal to the ratio of the radiuses, or in case if we were to express this more accurate, because we deleted pi, is the ratio of the areas. I'll just put it right there so you can see it. And is equal to the ratio of the height of the water that it started and the ratio of gravity. So if we were to find what would be, it is a long integration process for, let's say, like a cone or a sphere, we would find different equations. And if we were to test our equations compared to what we see, we would be able to see if our predictions are right or Bernoulli's principle is missing something.
So let's go back to the guys.
Slow down, slow down.
Hey, Brenda wins.
Brenda won. Brenda was the first. Kelly, is it Kelly?
It's me. It's me. I'm done.
Is it done?
He's done. Yeah, he's done.
Okay.
This is not fair. I literally chose that one.
So what happened, guys?
No idea.
What
I
happened?
lost.
Why did you
That was
lose?
like a swirl.
Yeah, it was
Okay, it could be. It could be. It's kind of like a swirl.
Just because both of them have little whirlpools in them.
Like when it's a whirlpool, it goes down faster now because the water has like a direction.
So in the experiment, many people were guessing it's because of the swirling, or it was because of the different things that happened. But if we actually went to develop with the ideas that we mentioned over before, we can develop different equations to determine how fast or how much time would take to drain each container in this case. And if we plot them out and do our theoretical results, and we also to compare them to our experimental results, we will see that the shapes kind of follow the same arc as they continue to move forward. However, what does change is the amount of time that they take. And this is because in reality, we will see different frictions, different viscosities that could influence the time that the water will fluctuate. But if we compare that to, or the ratios between the experimental and the ratios of the theoretical results, we'll see that they are actually pretty close together. So what does this tell us?
In conclusion, the exit velocity and the time it would take to empty a container is dependent on its geometry. But we saw that modeling the mechanics of fluids is a task that depends on more than just ideal conditions. In reality, fluid mechanics are dependent on aspects like friction and viscosity. However, this exercise has remained useful as it has taught a lot of how we could come up to solutions to challenging questions through ingenuity. This video just sets the foundation to the many applications of math and science. We want to give a special thanks to our physics lab teacher, Dr. Vola, for his time and dedication as our professor, and also to our cherished participants, Aurelie, Brenda, Lucas, and Kevin, and as well as our parents who sustain us to continue to learn more about our careers. Thanks for watching.